I was having this really vivid flashback the other day to my childhood living room.
Oh, yeah.
Yeah, I'm sitting on the carpet cross-legged and just glued to the TV, and my mom walks in and drops the classic line, "Don't sit so close, you'll get square eyes."
Oh, absolutely. It's the universal parenting mantra. You'll ruin your eyes. It's right up there with waiting an hour after eating before you swim.
Exactly. But here's the irony, right? Fast forward to today, and what are we doing? We're spending hundreds, sometimes thousands of dollars to literally strap high-definition screens 2 inches from our corneas.
It is funny how technology flips the script on us.
We aren't just sitting close anymore. We're wearing the TV.
True, but there actually is a valid point buried in that old advice. Because even with the best VR headsets on the market right now, I mean, the ones that cost more than my first car, if you look really, really closely, the illusion just completely breaks.
It's the, wait, what's the industry term for it?
The screen door effect?
Right, the screen door effect.
Precisely. It's that grid-like mesh you see overlaying the image. Because the screen is so close to your eye, you can actually see the black spaces between the pixels.
It's like looking at the world through a mosquito net.
Exactly. You're trying to be immersed in a rainforest or exploring Mars, but your brain keeps whispering, hey, you're just looking at a bunch of colored lights.
It is the ultimate immersion killer. It's like seeing the zipper on the alien suit in a bad 1950s sci-fi movie. But welcome to the Deep Dive Lab, everyone, because today we are zipping that suit up for good.
We really are.
We are looking at a stack of research that claims we are finally about to make the digital world look literally indistinguishable from the physical world.
It is a massive, massive leap forward. We aren't talking about a small incremental upgrade here. We're diving into a paper published online just recently on January 30th, 2026.
In the journal Nature Photonics, right?
That's the one.
And we definitely need to give a massive shout out to the brains behind this operation. We're talking about lead authors Wei Cao and Sentian.
And it's a huge collaborative effort, too. They worked with teams from Tiangong University, Fuzhou University, and Fudan University.
Serious heavy hitters.
Oh, yeah, this is heavy-hitting academic research.
And their mission for this research, to entirely smash the world record for screen resolution. And the way they did it is what blows my mind, because they didn't use $1 billion laser or some sci-fi anti-gravity beam.
No, they used the exact same physics that happens when I spill my morning coffee on a paper towel.
Capillary action.
Capillary action. It is elegant, it is simple,
Yeah.
and it might just change everything about how we see the digital world.
So let's unpack this for you guys listening. Before we get to the waffle iron, and yes, we are going to talk about waffles, we need to understand why this is such a hard problem to begin with. Like, why can't Samsung or Apple just make the pixels smaller? We have computer chips with transistors the size of literally atoms. Why are screens still so clunky?
That is the million-dollar question. And it comes down to the fundamental difference between making a chip and making a light. To make a computer chip, you etch silicon. It's a subtractive process. You're carving away material. But to make a screen, specifically the organic parts of an OLED or a QLED, you have to deposit material. You're adding layers.
So it's like painting versus carving.
Exactly. And right now, the industry standard for making these screens is surprisingly similar to an inkjet printer. The same kind that's sitting in your home office right now and is always out of magenta ink.
I have a deeply personal vendetta against that printer. But okay, so we are basically spraying ink.
Basically, yes.
Yeah.
You have nozzles that spray droplets of red, green, and blue material into specific spots. Now imagine you're trying to paint a wall with a spray can. Pretty easy, right?
Sure, broad strokes. Nothing to it.
Now imagine I hand you that exact same spray can and ask you to paint the Mona Lisa on a Post-it stamp.
Yeah, that's going to be a total disaster. The spray is too wide, it spatters everywhere. It's going to look like a Jackson Pollock painting, not Da Vinci.
And that is the physical limit we're hitting with displays right now. Inkjet printing is just too messy at the microscopic level. You can get to maybe a few hundred pixels per inch PPI.
Which is what our phones are at mostly.
Right. Maybe 1,000 PPI if you were pushing the absolute extreme limits of engineering. But for true VR, where the eye cannot physically see the dots, we need tens of thousands.
So the spray can is definitely out. But what about the method we use for those chips? Photolithography. That's super precise, isn't it?
It is incredibly precise, but it's violent.
Violent.
Yeah, it uses high-energy UV light and harsh chemicals to etch patterns. If you use that on silicon, it's totally fine. Silicon is tough. It can take a beating.
Right.
But the materials inside a QLED, the quantum dots, they're delicate organic structures.
Oh, so the chemicals would just melt them.
Or the UV light would completely degrade them. You'd end up with pixels that are tiny, sure, but they'd be dim or damaged or just dead on arrival.
So the industry has basically been stuck between a rock and a hard place. Either use the messy spray can and get low resolution, or use the harsh lasers and destroy the product.
Exactly. Enter the researchers from Tiangong, Fuzhou, and Fudan universities. They looked at this problem and essentially said, stop forcing it.
Stop fighting nature.
Right. They realized that trying to push the ink into place or burn it into place was just the wrong approach. They decided to let nature pull it into place instead.
And this is where we finally get to the waffle iron. The paper officially calls it Nanoimprint patterning via capillary self-assembly. But when I read the methodology, I just pictured making breakfast.
It is a surprisingly accurate analogy, actually. So instead of a nozzle spraying ink, they use a mold. It's made of a flexible silicone material called PDMS.
Okay.
And this mold has billions of tiny, tiny holes in it, nano holes.
So it's literally a waffle iron, but the little pockets are microscopic.
Exactly like a waffle iron. Now,
Yeah.
usually in manufacturing, if you want to fill a mold, you press down hard. You stramp it.
Right, to force the material into the shape.
But remember, pressure damages these delicate quantum dot materials.
So they don't crest it.
They barely touch it. They place the mold gently over a special ink solution containing the quantum dots, and then they just wait.
But they don't have to wait very long, do they?
Not at all.
Because of the secret sauce we mentioned earlier, capillary action.
Let's break that down for a second because it's a force we see every single day, but we rarely stop to think about it. Capillary action is the battle between cohesive forces, which is the liquid wanting to stick to itself, and adhesive forces, which is the liquid wanting to stick to a surface.
It's the paper towel effect.
Yes, perfectly said. If you dip the corner of a paper towel into a spill, you can watch the liquid defy gravity. It climbs up the fibers. Or think about giant redwood trees. How does water get from the roots to the leaves hundreds of feet up in the air? Capillary action.
So in this experiment, the quantum dot ink is the water, and the nanoholes in the mold are the tree roots.
Spot on. The ink is dissolved in a very specific solvent called N-octane. When the mold touches the liquid, the adhesive force of those tiny nanoholes is so strong that it literally sucks the ink up. It just zips right into the holes.
The paper actually mentioned the speed, and I had to reread the paragraph. It said the solvent evaporates and the holes fill in nanoseconds.
It's virtually instantaneous. It's not a machine forcing the liquid in against its will. The liquid wants to be there. It rushes in to fill the void.
It's like a vacuum, a nano vacuum.
And because it happens so incredibly fast and without any external pressure from a stamp, it's incredibly gentle. The quantum dots aren't crushed or burned. They just flow into their new homes.
Okay, so the process itself is very cool. It's like nature's printing press. But we have to talk about the results, because none of this matters if the final picture looks like a blocky 8-bit video game.
Oh, the results are the best part.
The number they achieved, I really feel like we need a drum roll for this.
Is a staggering number.
They achieved a pixel density of 169,333 PPI.
It's a number that is almost hard to visualize, honestly.
Well, let's try to visualize it for everyone. Listener, pull out your phone right now. Look at the screen. If you have a brand new, high-end flagship smartphone, that screen is probably around 460 or maybe 500 PPI.
And it looks incredibly sharp, right? You can't see the pixels.
Right, it looks like a solid image. This new tech from the paper is 169,333 PPI.
Meaning it is roughly 340 times denser than the phone in your hand.
340 times? That is just absurd.
At that density, the entire concept of a pixel ceases to exist for the human eye. Even under a standard microscope, you would struggle to see the separation. The screen door effect isn't just solved. The screen door has been vaporized and shot into the sun.
But just how small are we actually talking here? Give me a real-world comparison.
Okay, so the pixel size they achieved is sub 100 nanometers. For context, if you pull a single hair out of your head and look at it,
Okay, I'm imagining it.
that single strand of hair is about 80,000 nanometers wide.
Wow.
You could fit nearly 1,000 of these pixels side by side across the width of that one single strand of hair.
That is actually hard to comprehend. We're
Yeah.
approaching the molecular level at that point.
We really are. But there's another layer to this discovery that makes it so scientifically important. Because it's not just about making things small. Anyone can smash something into tiny pieces. It's about making them neat and organized.
This is where we need to talk about the coffee ring effect, which honestly sounds like my kitchen counter on a Monday morning.
It's a universal struggle, for sure. But in the world of printing, the coffee ring effect is a complete disaster. Think about when you spill a single drop of coffee and just let it dry on the table. What happens?
You get that dark brown ring on the outside edge, and the center is kind of light and just slightly stained.
Right. And that happens because evaporation is faster at the outer edges of the liquid drop. That uneven evaporation creates a flow, a current, inside the droplet that carries all the coffee particles to the edge. They just pile up there like driftwood washing onto a beach.
And if that happens to a microscopic pixel,
You get a donut of light. Bright edges and a dark, dead center. It looks terrible. The color's totally uneven, and it wastes a ton of energy.
so how did our nanoscale waffle iron solve the donut problem?
It's all about the fluid dynamics inside those tiny nanoholes. Because of the specific shape of the mold and the physics of that noctane solvent, they created an entirely different kind of flow called Marangoni flow.
Marangoni flow.
Yeah.
Sounds like a fancy pasta dish.
It really does. But instead of pushing particles to the edge like the coffee ring, this flow circulates them inwards. It actively mixes them. So as the solvent dries the quantum dots, which remember are these tiny glowing nanocrystals, they don't pile up at the edges, they self-assemble.
Self-assemble. That is the magic phrase right there.
It really is. Imagine dumping a giant bucket of tennis balls into a room, and instead of bouncing everywhere chaotically, they land in perfect rows, stacked neatly, without anyone ever touching them. That is exactly what happened inside these nanoholes. They formed a perfect, flat, uniform disk of light.
So we have tiny pixels and we have perfect pixels. But I have to play devil's advocate here for a second.
Go for it.
Usually when you shrink electronics down this much, they get really hot, they get super inefficient. It's called the efficiency droop, right?
Yes, that is the absolute bane of the micro-LED industry. Usually when you make an LED, that small surface defects take over. The electrons literally get lost, and instead of turning into light, they turn into heat. And let me tell you, nobody wants a tiny toaster strapped to their forehead in VR.
Definitely not. That sounds like a lawsuit waiting to happen.
But the team from Tiangong and Fuzhou seem to have cheated the system here. Their data shows that the red QLEDs maintained an external quantum efficiency, or EQE, of 17.0%, even at that sub-100 nanometer size.
Okay, for those of us who don't dream in physics equations every night, is 17% actually good?
It's excellent. It's comparable to the efficiency of the big, standard LEDs you'd find in a high-end TV. And the green and blue pixels perform brilliantly too, by the way. This is huge because it means you can have these hyper-realistic screens without draining your headset's battery in 10 minutes.
So we've got the density, the quality, and the efficiency. But I have to ask, is it just a lab trick? Like, did they just make one tiny glass slide to prove a point? Or is this actually a real display?
That is always the proof is in the pudding moment with these papers.
Right.
And they totally delivered.
Yeah.
They didn't just make dots on a slide. They built a fully working Active-Matrix display prototype.
Wait, they hooked it up and actually played video on it?
They did. They imprinted these micro QLEDs onto a thin film transistor backplane, which is basically the nervous system that tells the pixels when to light up. And it worked perfectly. But here's where it gets really fun. They also printed these pixels on P.
PT, that's the plastic used in water bottles, right?
Yes, polyethylene terephthalate. It's completely flexible.
Flexible screens.
Fully flexible. Because the pixels are so incredibly small and the layer so paper thin, you can bend and twist the plastic without breaking the image at all.
This changes the form factor of tech completely. Right now, VR headsets are these massive, bulky bricks on your face because they have to house rigid flat screens and then use heavy glass lenses to focus your eyes on them.
Exactly. If your screen is flexible and has this insane level of resolution, you just don't need the bulk anymore. You could wrap the display around the inside of a pair of lightweight sunglasses, or eventually maybe even a contact lens.
Or what about clothing?
Why not? This printing process is done at ambient temperature. You aren't baking it in an oven. You aren't etching it with highly corrosive acid. If you have the mold and the ink, you could potentially pattern this onto almost any smooth surface you want.
That's where this gets absolutely wild to me. We've been talking about VR headsets this whole time, but if you can print a display that is indistinguishable from reality onto a flexible sheet of plastic, you could wallpaper your entire office with it.
You could coat any surface. Imagine having a window in a basement apartment that looks out onto the Swiss Alps. And because the resolution is higher than your human eye can physically resolve, your brain would perceive it as a real physical window. The depth, the light, it would be completely seamless.
It's essentially the holodeck from Star Trek. But instead of projecting holograms into the middle of the room, we're just covering the walls in perfect invisible pixels.
And doing it cheaply. That's the real kicker here. We aren't building multi-billion-dollar semiconductor foundries to make these. We are using simple molds and capillary action. It's massively scalable, it uses less raw material, and it's so much faster.
It really feels like we are standing right on the edge of a new era. For the last 20 years, screens have always been about more pixels, brighter pixels, but this feels like a shift to invisible pixels.
I think that's the perfect way to phrase it. We are moving from the era of looking at a screen to the era of looking through a portal. The technology itself is finally removing itself from the equation.
It is absolutely incredible work by these researchers. So let's bring this back down to earth and recap for everyone listening because we've covered some pretty serious nanophysics today.
We definitely have. Let's hit the 3 big takeaways to lock this all in.
Number 1 is the method.
Right. The researchers completely ditched the high-tech lasers and messy inkjet sprays. They used a waffle iron-style mold and capillary action, that sponge effect, to let nature pull the ink into place in mere nanoseconds.
Number 2 is the record.
They hit a mind-blowing 169,333 pixels per inch. That is a number that just destroys absolutely anything currently on the consumer market. It is over 300 times denser than the smartphone in your pocket.
And finally, number 3 is the quality.
They solved the dreaded coffee ring effect and the efficiency droop all in one go.
Yeah.
These tiny pixels are bright, they save battery life, and they self-assemble into perfect flat layers.
Oh.
And they work on flexible, bendable plastic.
It really does feel like the main hardware barrier to true virtual reality is finally crumbling down.
It is. The limitations we face going forward are no longer about fundamental physics. They're just about engineering and scaling up the manufacturing.
So here is the thought I really want to leave you with today. And honestly, it's a bit of a trippy one.
I'm ready for it.
We spend so much time in tech circles debating the metaverse and digital escapism. And usually the main argument against it is that reality is just better because digital worlds look fake. They look glitchy. You can always see the pixels.
Right, that uncanny valley feeling. You always know you're jacked in.
But if this technology scales up, if we actually get to the point where I can coat my living room wall in a flexible display that is physically indistinguishable from a lush forest or a sunny beach or a cyberpunk cityscape, and it costs about as much as a couple coats of premium paint.
The distinction between real and digital really starts to blur.
Exactly. When the screen is completely indistinguishable from reality and it can cover literally any surface you want, will we still actually care about looking at the real world at all?
Wow. That is the ultimate philosophical question, isn't it? If your biological senses cannot tell the difference, is there really a difference?
I don't know about you, but the minute we sign off, I'm going to go stare at a real tree in my backyard for a while just to make sure it's actually real.
Good plan. Go touch some grass while you're at it.
Exactly. Thank you so much for joining us in the Deep Dive Lab today, everyone. Hopefully the next time you spill your morning coffee and see that annoying ring on the counter, you won't just see a mess. You'll see the exact physics that are building the future of virtual reality.
It has been an absolute pleasure to explore the cutting edge with you.
And hey, if you want to keep up with the future before it actually happens, make sure you smash that subscribe button like a quantum dot rushing into a nano hole.
Oh man, that was terrible.
I know, I tried. See you next time, everyone.